Right, so like we're gonna do the thing where you get a random Boolean function, and then you try to implement it using a multi-layer perceptron, but like people, normally people would be like, you should use gradient descent. But the problem with that is that it produces they're hard to interpret, and so we're gonna work with a principle that if you have a Boolean function and you have like a discrete set of inputs, some of them have to be like, some of them are labeled +1 and some of them are labeled -1. Here's a very good principle, which is that every layer in an MLP has to distinguish pairs of input, every pair of inputs that is separated by the function that the network is computing. And which means that at least one unit in every layer, for every, again, every distinguished pair, like inputs that receive different outputs by the target function, at least one unit in every layer has to, give a different output for every distinguished pair. Yeah. So that suggests an algorithm where to make an MLP, multi-layer perceptron, or a Ford layer, anyway, which is you pick your target function and then you you figure out every pair that is a distinguished pair, and then you start constructing the hidden layers, and you just you just randomly pick units, and then for each unit you check like how many of the distinguished pairs it separates, and yeah, I was gonna do like rather than like picking a random unit, it seems like you could it turns out that problem is actually NP hard to like to find a hyperplane that like maximizes the number of pairs that it's separating with respect to the target function. Yeah, but yeah, I was talking to ChatGPT about it, and it was like that's NP hard, you dummy. 4 seconds or less. I don't know what that means. anyway, yeah, like if you go to ChatGPT, it's like maximize, variation, max margin. Anyway, yeah, it says like it's non-convex, but it is NP-hard. I always forget about that. So anyway, yeah, we're just gonna pick random. I mean, it seems like there should be some heuristic to. Like, you know what you could do is you could like you just maintain a list of pairs that for each layer, input pairs that need to be distinguished, right? Like they don't have a single unit. Because a single unit like is going to distinguish a lot of pairs, presumably. So anyway, yeah, it seems like every time you add a new unit, you just pick a pair that isn't yet distinguished, and then it seems like you should be able to distinguish that pair. Yeah, because I mean, like you just pick, for the pair, you pick the indices where they differ, and yeah, like you just match those indices in the weight array. Yeah, I mean, like, are we gonna use weight arrays? Because I wasn't gonna use weight arrays, I was gonna use function tables. Function tables are way better. Yeah. No. Well, I mean, like, yeah. If we stick to like 4 dimensions, yeah. I mean, there's not that many linear threshold functions. So you can probably exhaustively search. You can probably exhaustively search. Yeah. Okay. Right. Right. So yeah. So we're just gonna keep adding units to each layer. Until every pair is distinguished. And now, like once you've completed a layer, you now have like a new representation of every input point, right? Oh yeah. Now I'm trying to figure out if we want to restrict. Like if we want to allow variable width. I mean, like if you allow variable width, then yeah, like you basically have to use the weight representation. Yeah. Right. So the overall idea is that you keep making these new layers, which the thing is that you get lucky if a undistinguished pair of inputs is mapped to the same activation, like this for the entire layer. Because then you have like less points that you're dealing with, and the less points you have, the more likely it is that you can linearly separate them. Right? Like that's what we're banking on. Is yeah, we just yeah. I mean that's the algorithm. It's a pretty it's not a very good algorithm. So but anyway, that's what we're going to implement. So it's going to be yeah. Also, I'm going to ask GPT to implement it for me. I think I'm thinking I wanna. So I don't know if I should start a new conversation with GPT or not. I think yeah, right, okay. Okay, yeah, okay. So I'm going to describe. Yeah, I think we should use the weight representation as opposed to the explicit function table. I'm also trying to figure out, like, do you need biases? Yeah, right. Not clear. I'm gonna do it without biases. So, take that. Okay, so the algorithm that we're gonna do, we're gonna pick a random Boolean function, like it's going to be, 2 power n inputs plus minus 1 output, and then like we have to somehow track distinguished pairs, and so what we do is we initialize like the current layer and then the current unit, aka neuron. I don't know what standard terminology is for that. And I think it's unit. And then so then for the current unit, we pick a pair arbitrarily that is not distinguished presently. And then you pick a weight array that distinguishes that pair. And then you check, I guess, like how many other pairs that also distinguishes. This is like a really stupid algorithm. But I think it's like it's interpretable. I mean, I don't know. And yeah, so you just keep doing that for a layer until all the pairs have been distinguished, and then like again, you now have like a new representation of the problem, because every input point now has like a new representation, and the like corresponding binary label. And it's like you got lucky though. I don't know how to like enforce, or like if you even need, I guess, like getting lucky. You get lucky if like non-distinguished pairs at least one, is mapped to the same representation, because then you have less points, and then like it becomes easier to linearly separate. And so like the stopping condition, like for an individual layer, is all of the distinguished points have at least one unit that distinguishes them. And then, right, and then that gives you like a new representation. The stopping point overall is your new representation, like actually linearly separable. And, yeah, how are you gonna figure that out? That's just, that's just a system of, that's actually, yeah, like that's like a system of inequalities. Because you're saying like for each point, does there exist a weight array that, like if the point is supposed to be +1, when you multiply by the weight array, do you get like greater than +1, because we're using like the sign SIGN function as nonlinearity. I think what if you just do gradient descent though? Like here's a question I don't know the answer to. Yeah, here's a good question, which is that if you have a system of linear inequalities that has a solution, is gradient descent guaranteed to find the solution? Like, is this, is this a convex problem? I don't know the answer to that. Let's see if GPT does. Okay. Like, if I have a system of linear inequalities, that has a solution, can gradient descent be used to find the solution, and is it guaranteed to find it? Okay, let's all see what the hell happens with that. You guys like systems of linear inequalities, isn't it? Yes. Yes, we do. Oh no, it's not gonna answer me. Ooh. Well, that's not good. Okay, what if I start a new conversation? Yeah. How do you do a new conversation? Like that? Alright. And, yeah. Okay, cool. Alright. There you go. There you go. Gradient descent needs an objective function. Okay, what's it saying? All stated for solid systems of linear inequalities. Linear inequalities typically defines a feasible region in a multidimensional space, often forming a polytope. Yeah. Gradient descent is to find local minimum or maximum of continuous differentiable from this. Okay, fine. There's no natural objective function to minimize. Yeah, gradient descent requires. Alright. Okay, fine. Traversing the vertices. Right. Yeah, but like, isn't I thought interior point like uses a gradient. Gradscent is not suitable for solving systems linear inequalities. Non-differentiable nature. Yeah, but isn't there like I guess I'm confusing it like with linear regression. Yeah, I'm like confusing it with linear regression. Okay, that's cool. Right. Okay, so you have to use like linear programming to right, for feasibility. Right, yeah. Okay, dang, man. That's not cool. Yeah, you have to do feasibility. Yeah, I forgot. Yeah, I remember how to do that. Like, you have to do, like, I don't know if I want to do that, though. That's way too complicated. Yeah, you know, I mean, okay, we could still just run gradient descent. You know. No, wait, like what, or I guess logistic regression, like, I mean, the problem setup is, the problem setup is we have like a single unit, and then we have this input-output mapping, and we're just trying to determine if the input-output mapping can be computed by a single unit. And, you know, the unit is, you know, the dot product weight vector with nonlinearity. And so you can run. Yeah, you can run gradient descent on that. I feel like that is a convex. Right. Okay, so like I'm trying to determine if an input-output mapping is representable with representable with a single neural net-like unit. Computing sigmoid WX or W is the optimization variables, and X is a binary input. Okay. W are the weights. No, I know, but I want to use gradient descent. God damn it. Yep. Linear combination. Yep, that's all good. Binary input space. Yes, this is all true. Single sigmoid unit can represent linearly separable functions. Well, if there's a hyperplane that separates the inputs. Yeah, I know. Check the desired output. Yeah, I know. No. Right. That's right. No, I want to use gradient descent, dude. Write down the equations for each input output. Yeah. Right. No, I know. Oh my god. Right. Yeah. If the mapping is linearly separable and I run gradient descent, with some appropriate objective function like like is this problem convex? I think I'm gonna run out of they don't, whatever it's called, budget. What do they call it? I don't know. The problem is convex. This is all I've been trying to establish. Yep. Yep. logistic regression. Sigmoid convexity. Right. Yep. Right. Positive semi-definite. Gradient descent. I know. Right. Yeah. Good. Okay. The mapping is linearly satisfied as appropriate convex objective function. Problem is convex. Gradient descent applied to this convex form is guaranteed to converge. Yeah. Right, that's all. Okay. Yeah, so we're saying like logistic regression is yeah, I don't understand the motivation for logistic regression. That has something to do with something to do with like entropy. Right. Yeah. What if I just use what if I just use square difference? Also, can you give a PyTorch code snippet of this? Am I gonna hit limits? What's the word for limits? Yeah, I can't think of the word. There's like a word for it, you know. Using the square difference just can lead to a convex problem. Yep. Oh no, it broke. Convexity. Right, exactly. This is convex. Exactly. I mean, like, what if you just iteratively do that for an MLP? I mean, yeah. Good. Two binary input features. Man, don't manually type out the... It still doesn't understand that I want binary output labels, but that's fine. Hopefully I can do one more query, because I wanted to write the whole algorithm. Right? The algorithm, for each layer, you have this explicit input-output mapping. Right, like the first layer is just all possible inputs. It's just the function itself. But then as you move through the layers, the representation changes. So anyway, you have this explicit input-output mapping, and the input-output mapping gives you like distinguished pairs, and then for each pair that is currently undistinguished by the layer, you pick a unit to distinguish that pair. You then determine how many other pairs are, like, you know, fortuitously also distinguished by that layer, by that unit. And you keep adding units until there are no more distinguished pairs that are not distinguished by the layer. Oh man, I broke it. Oh, dude. Oh, jeez, man. And, yeah, so then you just keep going, and then, oh yeah, but every time you have a new layer, it gives you explicitly like a new representation, and then the ending condition is you check linear separability of that new representation. And like we are in no way, you know, like trying to encourage linear separability. We're just trying to maintain distinguished pairs. And then that, you know, that produces presumably like huge neural nets. And then, you know, we can compare them to actual gradient descent neural nets. I'm gonna hit usage limits. I haven't accomplished anything so far. This is kind of annoying. Well, you know, okay, let's write some stuff. Adding best fit units until computes function. Indeed. Yeah, so, well, I could just try to, like, mock. I could try to, like, mock the code. Yeah, I'll just mock the code, see how that goes, or something. I don't know. Import numpy as in p. Import itertools it import PyTorches torch. Is that how you do that? PyTorches torch. Oh no, that's not how you do that. Okay. Alright, I think we're good there. And then so first of all, we have to pick a dimension for. Everybody loves dimension 4. Yeah, and so then we're going to pick a random target function. Yep. Pick random target function, TF. Yeah. Right. So dang. Let's just empty array. List IT product then right, I don't know, target function equals like input random choice -1 I don't know if the decimal thing matters is size equals or shape. Is it shape or size? 2 power n rows, 1 column. Is that cool? Print inputs. Oh no, it doesn't like that. Oh, it's size. I don't understand the difference between shape and size in P. Okay, these are inputs. I don't know if they need to be floats, whatever, who cares. Okay, and then print TF. Nice. Very nice. I can tell you already that this function is nonlinear because of these 4 rows. Right? Probably some other reasons also, yeah. Yeah, no, it's nonlinear. Right. Okay. So, and then we have like the current mapping, which is inputs, comma, TF, just binary labeling. And so then I guess like we want to turn that into a new representation. I mean, it kind of seems like you... It kind of seems like it'd make... like, instead of using, like, random functions... Well, no, I mean, the original idea was, like... You... pick a distinguished pair. It seems like it would make more sense to... like, try to fit a unit... you know, to this function, even though it's not possible. And then, right, so, okay, so then that would give you, like, a unit in the layer. Yeah, I mean, it's not really clear what you would do after that. Like, I mean, if I have, like, the best fitting LTF to a given, to the target function, I mean, like, so it's like, okay, some of the inputs it's correct on, some of them it's incorrect on. What would you do? I mean, like, the incorrect inputs, I mean, like, I mean, you could create, like, a new training set where you just have the incorrect inputs. And then you could try to fit again, which would be easier because it's less points. And I guess you could progressively do that where like you'd end up with a layer that like has a unit, like every input is correctly computed, the output is correctly computed by at least one unit in the layer. But it's not clear how it's not clear that, like, how is that useful though? Yeah, so we'll just stick to the original. We'll just stick to the OG algo. Which is, we just try to maintain distinguished pairs. And, right, so, yeah, okay, okay, so anyway, but like we have something like, you know, current representation is just the pair of inputs, outputs. Maintaining. Is that how you spell that? Maintaining. Huh. That doesn't seem right. Distinguished pairs. Okay, so like compute distinguished pairs. So we're gonna compute distinguished pairs. And like, what's the best way of doing that? I mean, you could just maintain a like that's you maintain like a binary matrix with inputs on rows and columns. And then no, well actually, yeah, you okay, you could do, yeah, you could do a binary matrix where the rows are inputs that are accepted by the function, like +1 inputs, and the columns are -1 inputs, right? So then every entry is by definition a distinguished pair. And then, yeah, you can just like index into the, you know, so like it's initialized with zeros, I guess, and then you just search for the first 0, and then that will I'll explicitly give you a pair, and you know, like given a pair of inputs, it's like easy to find a weight array that distinguishes them because you know, just the indices where they differ, you just match one of the sign pattern of one of the inputs. And then I guess like, yeah, like everything else is 0. So then, yeah. So you do that, and then you check. I mean, they'll give you a weight array, which will give you like an explicit function. And you know, then you check if you get like any free pairs. And yeah, and then you just keep doing that, and then you'll have like a whole new representation. Okay. So yeah, okay. I wonder how much of that I can get GPT to write for me, because but it's also like you could do like a hybrid thing, because how long have I been going here? This is probably too long. Yeah, okay, that was like an hour. Yeah, we will continue this